Welcome to the lesson video on shrinkage. Shrinkage in multivariate linear regression is a process of shrinking or decreasing in size the coefficients for less important regressor variables. So this is similar to model selection or subset selection that we've done previously. And in subset selection, we reject some of the variables completely, and when we do our linear regression with the remaining one. And those variables that we reject that we're not going to use, we can think of those as low important variables. That's the process of model selection or subset selection. In shrinkage, instead of eliminating the variables completely, we're going to optimize things in a way that decreases coefficients for those variables. So there's two main shrinkage methods. So there's ridge regression, and a ridge regression pushes down the coefficients for low importance variables, and then lasso regression. And the way both of these methods work is they're going to optimize, they're going to choose coefficients that minimize the mean squared error, but also minimize a penalty on the coefficient size. So there's ridge regression, and then lasso regression has the advantage. And so here's the resulting difference. We'll look at the formulas in a moment. In lasso regression, it will tend to push some of the coefficients all the way down to zero. In ridge regression, the coefficients don't generally get to zero, they just go down. And in lasso, they tend to arrive at zero. And so here's shrinkage methods. So first, let's start with regular least squares regression. And in least squares regression, this is a review, we're going to find the coefficients beta naught through beta p that minimize the residual sum of squares error. So what you look at is the residual sum of squares error right there, and there's a familiar formula for residual sum of squares error. Here's how ridge regression works. We're going to do this something very similar to least squares regression. We want to find the coefficients that minimize this, the residual sum of squares error plus a penalty term. And so the formula is down here, RSS plus, so residual sum of squares, and then plus this penalty term. And in lasso, we're going to do the same thing. We're going to find those coefficients that minimize our residual sum of squares plus the penalty term. And if you look at the difference between ridge regression has this lambda times the sum of the coefficients squared, and then lasso has the lambda times the sum of the absolute value. So in either case, this sum measures the total magnitude of all the coefficients. So it tends to push the coefficients down towards zero when those coefficients don't increase when those coefficients don't add to the decrease in residual sum of squares much, they'll get decreased in that sum. And so on the left-hand side for each of these, you have the residual sum of squares error term. So we're optimizing, or we're picking coefficients that will make that small. But in ridge regression and lasso regression, we have this penalty term. And so that penalty term penalizes for large coefficients. So if the coefficients are all large, that penalty term is large, and those would be coefficients that won't be chosen. And so you can think of this as similar. These formulas are similar to when we look at BIC or AIC. A lot of things have one term that measures goodness of fit, and then a penalty term that for something that we want to reduce. In AIC and BIC, we were reducing the total number of regressors, and in these formulas, we are trying to reduce the total amount of coefficients. And just one more comment here, when you're doing least squares regression, you can solve for these coefficients explicitly. When you're doing either ridge regression or lasso regression, these shrinkage methods, you can't find these coefficients explicitly in general. There has to be an iterative search that will solve for them. The other thing that's worth looking at on this formula, these lambdas, those lambdas control how much we're going to weight the size of the coefficients. When that lambda is large, the size of the coefficients becomes very strong, and that becomes more important than getting low fit. If lambda is small, then the size of the coefficients doesn't matter as much, and it tries to get a good fit measured by residual sum of squares error. And of course, when lambda is zero, we just recover normal least squares regression. Okay, so let's look at some plots. On the vertical axis, we have the standard coefficients in each of these plots. standardized coefficients. And on the left-hand plots, this is ridge regression. On the right-hand plot, it's lasso regression. And so we're going to look at those standard coefficients on the vertical axis as a function of this lambda on the horizontal axis. And remember, lambda measures how strong of a penalty we're going to have on the coefficient size. So the larger lambda is, the smaller our total coefficients are going to be. And so you can see on ridge regression, this plot on the left-hand side, initially here, that's the least squares model, just ordinary least squares. And then as lambda increases, we have an increasing penalty on the size. And then presumably the good models would be in this range here. Over on the right-hand plot, if we look at lasso, again, when lambda is 0, we are looking at the ordinary least squares regression model. And over here on the lasso, if you look at, say, lambda being somewhere between 200 and 500, let's look like right here, let's say at 500. Look at those coefficients. The coefficients for the gray variables, these are the ones that aren't very important, they're now have gotten to 0. And so that's one advantage of a lasso. We reduce those and they'll get all the way down to 0. And as you look to the right, let's pick it, a value here. The coefficient for the black variable, that's income, has gotten to 0. And the only variables that are left at that point are credit limit, rating, and student. And so we can see some of the nice features of lasso that it pushes the coefficients all the way to 0. So how do we choose a value for lambda? On the left-hand plot, we can look at a function of mean squared error for cross-validation based on lambda, and this is for simulated data. And so the way we choose lambda is cross-validation. And as with a lot of things, a lot of parameters, we'll pick the value that gives us the least cross-validation error. And so this curve here that is reddish colored, this is the textbook figure 6.8. They call it purple. I don't know, it looks raspberry to me or something, maybe lavender, but okay, whichever. But that curve is the test mean squared error, and then this point that's xed on the curve is where we get minimum error, and then we would pick lambda to be whatever the value is that's right below that. Since this is artificially created data, there's one nice thing that we'll point out here. There's a black curve. The black curve is squared bias, and so that's bias error. So that's error that's coming about because of the bias in the model. And then in green, we have the curve which is variance or error from the variance. And so at the one extreme, we're doing ordinary least squares, we have more error from variance and less from bias. And at the other extreme, we have more error from bias and less from variance. We have more variance and less bias at this extreme because we have all our predictors available. And so we're not going to have as much bias. Out at this extreme, we don't have as many predictor variables available, and so we're going to have less variance, error, and squared bias. So this spectrum between these two extremes is what we think about when we think about the bias variance trade-off. At one extreme, high bias, low variance. At the other extreme, it's the other way around, and generally we want something in the middle. And so one of the things these shrinkage methods do is they allow us to do regression, and you could think about it as giving you some measure of trade-off and finding a balance between those two types of error. So review shrinkage. Shrinkage is a method for doing linear regression in which the coefficients for low important variables are pushed down towards 0. You can think about it as all the things that we do subset selection for to help us out. Shrinkage does the same things, but the only difference is that you're picking a lambda instead of eliminating variables entirely. And in two methods for shrinkage that we've looked at, ridge regression and lasso regression, the computation of the coefficients minimizes the error plus a penalty on the size of the coefficients. And this is a good, when you think about shrinkage, you think about this is what's driving things. You have an error and then plus this penalty on the total size of the coefficients. And so that tries to minimize the error and also minimize the total size of the coefficients, and it's competing those against each other. Thank you very much.